This video will cover Chapter 17, Sensitivity Analysis, and focuses in on the intuition of the Greeks. We'll look at Greeks relative to moneyness and Greeks over time. In other words, as the option matures. We'll tend to focus on call options, but I'll have a little bit of put action in the discussion also. First thing we want to do is look at delta. The delta of an option, how the call changes relative to the stock price. And we can graph that out. It looks something like this is the delta with respect to moneyness. Now this is moneyness. Because we're looking at, somewhere here is K, and we're looking at relative moneyness. And this is going to be 1.0, and this is ND of 1, which is equal to delta. And basically what this line is telling us is this is how delta behaves over time. Or, I'm sorry, over the option value here. Okay? And so what it's doing is it's mapping out the slope. The slope of this line is measured on this line. So it's kind of, you got to really think about this if you're not used to seeing it. But if you wanted to measure the slope, here's the slope is basically flat. It's almost zero, so it's almost zero here. The slope gets steeper and steeper, and so you start going up in this direction as you start going in this direction with the stock price. Here's the call. Until you get to a point where the slope flattens out at 1, which is what it's doing here. It's approaching 1 as we go. Okay. Now, delta hedging, which is really the intuition behind the Black-Scholes model, and we saw in the binomial. Remember, we delta hedged in the binomial, and we were able to see that, look, if you have delta, the right number of shares of stock, you can create a riskless hedge. That's how we valued options. And so delta hedging works only for small changes in the stock price. If you have large changes in stock prices, which is quite common, by the way, in the real world, you have jumps. Stock prices often jump and they're discontinuous, and they can be quite volatile. Then you need to reflect gamma. And gamma is curvature. And so here we have gamma. And the curvature peaks out when you're around K. When you're about at the money, curvature peaks out. And so again, we're looking at relative to moneyness. Where is gamma the highest? Now gamma is not very big when the option is deep in or out of the money. It's largest where the stock is at the money, because that's where the curvature, see if I can exaggerate it as best I can. Here's where the curvature is going to lie, right here. Okay, right when you're close to K. So if you can delta gamma hedge, then you're in a good position. Not only are you going to reflect this linear relationship with respect to delta, but you're going to capture most of this curvature, not all of it, but almost all of it. Okay, and this curvature is going to be, will always be positive for a call or a put. And so what it says is, if the stock is volatile, you're going to benefit from volatility in this case by owning calls and puts. Now, this curvature changes over time. Now, let's look at it from a time dimension. A call price looks something like this when it has a lot of time left. And when time starts to decay and there's less and less time, you start to kink. Obviously, this starts to kink. So here you got an intermediate time. And here you start to kink, because eventually it's got to mold into this hockey stick that we have here. And so your curvature right here is going to be very, very high as that kink starts to form. Now, the next one is theta. Theta is a bit interesting here. Theta for a call is always negative. So here is negative, and here the more negative you go. And here is going to be K. Theta is going to be the most negative. In other words, you're going to get the most time decay out of an option as when the stock and the strike are about equal. You know, when the option is about at the money. And when the option is deep in or out of the money, here or here, there's not much time decay because there's not much insurance value at those points in time, or at these points in the stock price. We can see why time decay is largest when we're near or at the money, and that's because when you're near or at the money, right here, this is the area of greatest value for the option. It has the greatest insurance value at that point. And so when options decay, really you have an impact from time value component, but you also have a large impact from insurance value, because the insurance value happens to be greatest when the stock is about at the strike, because that's when it has its best ability to hedge the underlying stock. And now with put options, you can actually have positive theta. So puts often can look like this. And so that's the theta of a put. Now deep in the money puts can actually have time growth. That's what that says, time growth. And so I can show you that here in a second here. How do we have time growth with a put? Well, with a put, so I put a P up here, you have the hockey stick for an American. Remember, that was a boundary condition. But with a European, since a European put delays the receipt of cash from the strike, the value will be less than an American. And so you can have an option price that's below the value of the American. It won't be below a European. Nothing can go below this dotted line. But what will happen is, as time goes on and you get closer to maturity, what happens is you get your option price actually grows in value. Okay? And it'll grow and grow and grow until you get up to this line. Notice how it kind of nothing happens over here when you're at or out of the money with the put. In terms of growth, the growth will happen. The slope of this line will change, and it will eventually grow to this point. So that's put options and how they can have positive time growth. And you can get that action. You can if you have software from the internet, you can, if you plugged in S equaled 5, for example, and a K of 12, you have a deep in the money put, right? Sigma 35, and you were to put T of 1/2, half a year option, put in an R of, say, really high, 15%, because what we need to do is we need to have that, the time value effect, that growth from opportunity cost coming in the play, and so you make R high, the interest rate high, and that's when you're going to get that time growth. Theta, by the way, here will be 1.6654 positive in this circumstance, and you'll get this action here. And you'd see if you were to change this stock price to, say, 15, so put a 1 here, 15, you would find that the theta would be negative in this area, and it would actually drop down a bit. Okay, one more thing with time decay, which is important, especially in stock track and in the real world, obviously, is that as you go through, this is time value and insurance value. So what I'm saying is, you're back to calls, you have intrinsic value plus time value, right, plus insurance value. And so I'm capturing both of these are influenced by time. Obviously, time value is influenced, but so is the insurance value. And so what we're saying is options that are close to maturity decay the most. That's why you have this big steep negative slope. And when you have an option that's a long way off, right, so you're right here at time t and it's a long way off to maturity, the option will decay, but barely. Let's keep that in mind. If you buy an option, options that are very short maturities are really cheap, but they decline in value quickly. Okay, let's look at Vega. Okay, Vega describes how option prices change with respect to a change in volatility. Now, technically, according to the assumptions of the Black-Scholes model and the binomial option pricing model we used, the assumption was that volatility was constant over the life of the option, which means the volatility of the underlying stock remained constant over its life. So what we're doing is we're looking at these changes in, what would happen if we changed volatility. Technically, it violates an underlying assumption, but nevertheless, you'll find a ton of literature on this. And the textbook talks about it quite in length. People still want to know, even though it kind of violates the underlying assumptions of the model, what happens when you change volatility. So first off, let's look at volatility relative, the effect of volatility relative to moneyness. And so when you have high volatility, you have high option prices. Okay, so here's sigma high. You have a slightly less, say high, sigma medium. You'll have a lower price. And when you have sigma low, low volatility, you'll have a low price relative to the strike. Okay. Now, how does volatility stack up relative to moneyness? So kind of you can see that in moneyness in the price, but how does Vega itself work? Well, it looks something like this. Okay, Vega is highest around the strike, which means the option has really what it's saying is the option is most affected by changes in volatility when you're at or around K. Which makes sense because when you're right here, you have the most insurance value with respect to the option, the most insurance value here, and so this area will change the most, is what this is saying, for changes in option value. Changes in volatility. Okay, now, let's look at rho, the last one. And so rho looks like this with respect to high and low interest rates. For a call, here's a high rho, so here's R, RH, meaning interest rates are high, calls are worth a lot of money. Remember that story that I went into with the plus and minus table at the end of one of the chapters where I said, look, a call is a substitute for buying a stock long. And if you buy a call, the call itself is far cheaper than the stock usually, which means the opportunity cost of money associated with buying a call is less. And so calls are more valuable, all else being equal. So when interest rates are high, calls are worth a lot. When you have an in-between interest rate, say RM, then you have a lower option price. And when interest rates are low, you have low option prices. Okay. Now, what's interesting here is rho. Here we have rho with respect to stock prices. Let's actually graph rho. For call options, rho looks like this. So rho is positive with call options. So this is rho C, okay, and you have a rho with put for a put looks like this. And so this is rho with a P here. And what it's saying is, look, focus on these two areas. What it's saying is, when you have calls that are deep out of the money and puts that are deep out of the money, there's almost no effects because you're almost at zero in terms of changes in interest rates. Interest rates have almost no effect on deep out of the money options. Now, why is that? Well, when an option's deep out of the money, it has almost no value. So there's no opportunity cost issues with respect to changing interest rates. And so there's very little effect. Now, when the call is deep in the money here and the put is deep in the money, those options are expensive, and so there's a high degree of interest rate sensitivity with respect to that. Notice how the put is always negative, because remember, we looked at the case when, the plus and minus table, a put is a substitute for shorting a stock. And if you short a stock, your broker sells the shares, puts the money in the account that earns an interest rate. And when interest rates go up, short selling becomes very attractive, more attractive than the put, relatively speaking. And so puts go down in value. And so there's a negative relationship, which is why this graph here, this line, is below zero. Okay. Now, that's basically it for the intuition behind the various Greeks by themselves. Now, there's a lot of literature on Greeks, quite a lot of it. And I'm not talking just math. I'm talking about a lot of concepts where they look at ratios and combinations of Greeks. And one interesting combination is called the gamma-theta trade-off. Okay. Now, gamma is always high and positive, right? It's always positive. I shouldn't say high and positive. Gamma is always positive. Okay. And theta is typically negative. Okay. Since gamma is positive, you can profit from volatility. So let me try to exaggerate here. So here you have a call that's at the money right here, and you have a lot of volatility in the underlying stock. It's bouncing back and forth here. You have this gamma right here. Gamma is measuring most of this distance, not all of this distance. Most of this distance is measured with gamma. And so that's positive effects from gamma. So when volatility picks up, option prices increase, all else being equal because of that, call options. Now, keep in mind that in order to capture this gamma, you need to be close to K. Right? But what did we just learn with theta? Well, time to K is greatest because you got the biggest gap here, which means you have the biggest distance between the payoff at expiration and the value of the option. It's biggest right when you're at K here. So what you're doing is you're looking at, if you want to get gamma, high gamma, which means you want to capture volatility and the positive effects, you're going to pay the price through theta because you're going to have a high time decay. And so it offsets that effect.